Hello all. Today we're going to be doing 7.1, which is the start of exponential equations and graphs. We're going to start off with our exponential function, which is y is equal to a times b to the x power. Biggest things to highlight from here is x is now in the power. That controls how many times we multiply something by itself, or if the power is negative, we need to put in the denominator or wherever it needs to be. The a value is our coefficient. This is going to control if this is a vertical stretch, a vertical shrink, if we're going to flip our graph. But the big kicker here is our base, which sometimes can be replaced with rate, but we're going to get to that in a little bit. The base is really important. If it's bigger than 1, then it's going to be a growth. If it's less than 1 but bigger than 0, it's going to be a decay. And to start this off, we're just going to graph a few functions. We're going to do 2 to the 0 power, which is 1, 2 to the first power, which is 2, 2 to the second power, 4, 2 to the third power, which is 8. And I'm going to graph these out. So you can notice that anything to the 0 power is going to be 1. 2 to the first power is 2, then square it's 4, then cubed it's 8. But if we look at this pattern going backwards, we can see that we're cutting our values in half. 8 cut in half is 4. 4 cut in half is 2, 2 cut in half is 1, and so if we think about this in a different sense, then we're going to have to realize what we're doing here is we're either doubling or cutting things in half, or if I have a negative power, I have the reciprocal value of 1. So negative 1 right here is the reciprocal, its output is the reciprocal of 2, which is 1/2. If I go to negative 2, the reciprocal power is 4, so it's 1/4. So if I go 1/2, then I go to 1/4, and I'll go to 1/8, and then 1/16. You can see I'm getting closer and closer to y is equal to 0, but I will never touch it. We call that an asymptote, a horizontal asymptote in this situation. But let's go again with this reciprocity, this reciprocal. Not reciprocity, I apologize, wrong terminology. 3 to the 0 power, still 1. Let me use blue for this one. Still 1. 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. So again, we start off at 1, then I go up to 3, then it goes 9, and then not graphable from this point. But I'm going to have to use the idea of negative powers do not reflect negative numbers. 3 to the negative first power is saying I have 1 3 in the denominator. If I have 3 to the negative 2 power, that means I have 2 3s in the denominator, or 1/3 and 1/9. So again, same kind of idea here. I've got a third, and then I've got a 9th, and then I'll have a 1/27th, and then 1/81st. I'm getting really close to that value of y equals 0, but never actually getting there. So let's do x to the 1/3 this time. And you'll see this graph's going to look a little different. So anything to 0 power is 1. 1/3 to the first power is a third. 1/3 to the second power is a 9th. 1/3 to the third power is 1/27th. So I'm going to graph these. I got 1/3, then I got 1/9, then I have 1/27th, and 1/81st. But if I go backwards, I'm going to use the reciprocal of those values. So 1/3 to the negative first power is 3. 1/3 to the negative second power is actually 9. So going backwards, it looks exactly like my x, or 3 to the x power graph, but reflected over that x equals 0, or the x-axis. So let's try the last one. Our last problem has an a value of 2, so whatever we put in, we have to multiply by 2. So 3 to the 0 power is 1, but 1 times 2 is 2. 3 to the first power is 3, times 2 is 6. And essentially, we're just doubling these values here. So 18, 54, 2/3, 2/9. Looks very similar. But this time, when we go about these points, we've been stretched by 2. Still an exponential equation, still a growth, just a vertical stretch. So on to the next. 'An asymptote. 'An asymptote is a line that the graph approaches as it is either increasing or decreasing, but never actually touches, or you can put crosses. And this is true for vertical asymptotes. Horizontal asymptotes are a little finicky in this sense. We can get to that, we can talk about that a little bit later, but horizontal asymptotes are a little different than vertical asymptotes. Let's talk about growth and decays with exponential values. If our a value is greater than 0 and our b value is also greater than 1, then the function represents an exponential growth. Just like our y equals 2 to the x power, y equals 3 to the x power, and then y is equal to 2 times 3 to the x power. If the a value is greater than 0, but the b value is less than 1 and greater than 0, then this represents an exponential decay. And we can see that with our fractional or rational base raised to the x power. That was the purple line on the graph. Okay, let's just try this right here. There's a little mistake on D. There should be an x power right there. We can see that 0.95 is less than 1, even though our a value is greater than 0, so this creates a decay. Again, our base value on B is a quarter, or 0.25, so that is also a decay. Now, on C, our base is 2, so it's double, so we're going to do 2 to the x power, and our a value is still greater than 0, which is good. We have a vertical shrink in this situation, but this will be a growth because our base is greater than 1. Last problem, 1.8 is greater than 1. Therefore, this must be a growth. All right, moving on. We need to talk about how we're going to write percentages. Just like we did before, you saw that we had 1.8. Well, that's 180%. So we're going to rewrite these as decimals. When we talk about percentages, we're going to always rewrite them as decimals. And when we talk about exponential growth by a constant percentage over each time period, we start off with 100%, or 100% plus the rate percentage. But we translate it as 1 plus the rate, and the rate must be in decimals. If we have a decay, so this was for a growth, we're going to be adding. If we have a decay, we're going to be subtracting. We're going to be subtracting these things. So you can see with this example of a 2% growth rate, we are going to add 0.02 to 1, because it's essentially, thinking about it this way, 100% plus 2% equals 102%. But since this is a decimal, we need to move it twice, and we get 1.02 as our b value. So this would be our b value. If I have a decay, I'm not going to be adding, I'll be subtracting, and I won't end up with anything greater than 1. I should end up with less than 1, which I do. End up with 0.98 if I take away 2%. So let's try it a couple times. A growth rate of 3% is really 0.3, so it's going to be 0.03, I apologize. So it should be 1.03 is our growth rate. A decay rate of 0.03 is going to end up as 0.97. A growth rate of 30% is actually 0.3, so I'm going to add it onto 1, so it's 1.3. The decay rate of 30% is 0.3, but this time it's going to be negative, so it ends up with 1 minus 0.3, which is going to be 0.7. So now, looking at these following problems, we're going to talk about writing exponential functions, and we're going to be using growths and decays. So on practice 1, we have a population, an a value, this is our a value, and it grows 1.3% each year. So we're going to change that immediately to a decimal, so it would be 0.013, and we're going to try to grow this for 10 years. So first we're going to write an equation. Y is equal to 1,236,000 times 1.013. So it's going to be a growth, because it's above 1, of 1.3%, and it's going to be raised to the x power. The only thing we need to do now is plug this in the calculator. where x is our time, and we're going to substitute in 10 for our x. So I'm going to grab my calculator. And it depends on which calculator you're using, but this is really just a calculator problem. And when I plug it all in, so I'm going to multiply by 1.013 raised to the 10th power, I'm going to get a growth over 10 years to a population of 1,406,413 people. And this one has a decimal in it, but I'm going to assume that you can't have 1/16 or 16% of a person, so I'm going to round down. Some people will round up, some people will round down. Again, this is a population, so the population. Okay, on number 2, we have a new car. In this case, I changed this cost to $38,000 in my class, but I'll keep it as $18,000 just in case. So we have an A value of $18,000, and it's going to depreciate 25% or 0.25 each year. So if I'm writing my equation, I'm going to start off with my A value, which is 18,000, and I'm going to multiply by 0.75. I'm going to highlight this. So now you know it definitely depreciates or decays because it's less than 1, and it decays by 25% each year. So here's the understanding behind this. If it depreciates 25% each year, then we keep 75% of its value each year. So it retains 75% of its value because it depreciates 25% each year. So this is again a calculator problem. I'm going to plug into my calculator this. 18,000 times 0.75 raised to the 4th power. I'm going to do that right now, times 0.75 raised to the 4th power. And so after 4 years, this $18,000 car that you bought it as is now $5,695.31. I rounded to the 10th or to the 100th because this is money. All right, so we got through with just rewriting equations, but this time, what happens if you know populations or know your A value and your outcome, but you don't know your actual rate? Well, we can use all these things to figure out the rate. It takes a little bit more time, but unfortunately, you guys don't know how to do logarithms, and that's part of 7.3, so we'll get there. So we got to do a little bit of the longer way. So I have some values that I have to identify. I need to identify our initial value. I need to identify how long it takes. And then I need to identify the present value. So this is really, really important. So we have a couple things that we're looking for. We're looking for time, value when we start, and value when we end. So I'm going to highlight these accordingly. I have in 2004, here's our first time. And I'm going to write this. This is time when it's 0. Okay. There were 1,570 bears. So this is our initial value right here. Okay. In Denali National Park. In 2017, all right, there's a change in time. In this case, this time value is now 3 years later. The population increased, ooh, that's good, increased to 1,884 bears. We need to write an exponential function to represent this situation. Then we need to figure out how many bears there will be in 2025, and then we'll just need to try to do some guess and check to see when we will double. So that's the last important one. So let's set this up. Present value, which is 1,884 bears, is equal to the initial value, which is 1,570, times our base, or what we're going to be growing by, raised to the time. So I'm actually going to switch this t to be 3 years, because that's how many years it took to go from 1,570 to 1,884. This is now an algebra problem. I'm going to divide both sides by 1,570. And if I do that, 1884 divided by 1,570 is 1.2. That's a really nice number. Is equal to b to the 3rd power. How we get rid of the cube is to use a cube root. So I'm now going to cube root 1.2. And when I cube root 1.2, I end up with 1.062652. I'm going to round to the nearest thousand, so I'm going to do 0.63. And this right here is where you have to use your brain now. I know, hard, but have to use our brains. The 0.063 is actually going to get you 6.3%. So this is now our base increase each year, even though our b value is 1.063. Our rate of growth is actually 6.3% population growth each year, which is pretty good for bear populace. So now that we have our base, we can do fun things like ask how many bears there will be in 2025. If that's the case, in 2025, this means our t value is 11 years in the future. So I'm just going to go and plug this in. 1,570 times 1.063 raised to the 11th power. And if I do this, I end up with a population. So my population of bears is going to be equal to 3,074. And then it has some decimal, but I don't think we can have 4/10 of a bear, even if you're counting bear cubs. I'm going to count bear cubs as whole bears. Okay, that's good. I want to know now, so this one's done, I want to know when it'll double, the population will double. Well, 1,570 times 2 is 3,140 bears. Yeah, 3,140 bears. So I want to know approximately what time this will be. And I'm assuming that's going to be the 12th year. So I'm going to try this again. I'm going to go up to my calculator, and I'm going to put in 1,570 times 1.063 raised to the 12th power. And I was right, so the 12th year we're actually going to have 3,268 bears. So it's going to happen sometimes between the 11th and the 12th year when we will find when the population will double. Okay, this video is a long one and it covers a lot for 7.1. So make sure you're pausing, taking a break, and going back and watching this video a few times, maybe at 1.5 speed or 2 speed. If you have any questions, please feel free to contact me or one of my peers, and I hope you have a wonderful day.